Thank you. Okay, so I have included in the presentation more slides than the ones that we can actually discuss here in these 30 minutes, but you can use or consult the material for further reference if you wish. So I will present in a few words the totem experiment, the detector. Then we will have a look through what we call the totem special runs, often totem and alpha special runs together, because they need to have special tuned conditions of the LHC machine. And then some of the totem results, starting from the proton-proton elastic scattering differential cross-section, and then the more recent total elastic and inelastic cross-sections measured by totem at 7 and at 8 TeV. Finally, we will conclude with some perspectives on forward and diffractive physics, which are an essential part of the totem physics program, and that will be tackled with the data that we have taken lately this year, and hopefully we will analyze in the next months. So let's start with the totem experiment. Then, first of all, an overview of the physics program. Initially, there was a large uncertainty on the high energy evolution of the total cross-section, of the proton-proton total cross-section, with the data coming only from the cosmic rays. The Tevatron data was taken in the TeV region. In addition, had two slightly inconsistent measurements for which it was even more important to constrain the evolution of the cross-section with an additional point at 7 TeV. Then, of course, the elastic scattering is important to probe the proton structure. We measure it as function of T. Of course, it can be transformed into the space of the impact parameter. And then forward physics for the cosmic rays again. And that's why there is some synergy also with experiments like Auger. And as I said before, diffraction. Soft diffraction can be done by totem standalone, while for hard diffraction and jet production, totem has to analyze the data, take the data and analyze the data together with CMS, so that at IP5 we have a complete, full coverage detector apparatus. I did something that I should have not done. Okay, sorry. Okay, the experimental setup, how does it look like? So we are at IP5, you see the full CMS cut view, and then totem is half an experiment and half a machine device, if you want. Why? Because it has in the end caps of the CMS detector two tracking telescopes, T1 and T2, not by accident in front of CMS calorimeters, HF and Castor respectively, covering very forward eta ranges, as you can see from here. In particular, T2, to give you the idea, 95% of the cross-section is already visible in this eta range, so we are really looking forward. But that's not the whole story. Totem has also different sets of Raman pot detectors located at 147 meters and 220 meters respectively during along the LHC beam pipe, of course on the outgoing beams side. These are silicon detectors that we call edgeless, because in order to maximize the approach to the beam, to minimize the distance of approach to the beam, of course you don't want to have dead regions. And these are the detectors with which we measure the outgoing protons in the elastic or diffractive interactions. Okay, so as you can see from here, the key totem detectors can be 200 meters away even from IP5. This makes it such that these detectors are operated as machine devices, as collimators from several points of view, while these ones are operated as the CMS detectors, de facto. So, just couple of pictures. You see the two telescopes here, and an example of the Roman pots. Here you see along the beam, the installation. This is instead a close-up of the plates of silicon detectors that are present as stacks in each of the Roman pots. We have a quite interesting lever arm, as you can imagine, because we have pots that are installed at 5 meters with distance between each station. And this opens up a thing that is by far not obvious. When we say that with Totem we measure angles or scattering angles, we don't measure them in the traditional sense of measuring the angles at which the particles were scattered. When we say that with Totem we measure the angles, the angles, the particles, the tracks, the protons that you measure at Roman pots have traversed an intense list of magnets of LHC. So they go through not only not through a straight line, but not even a classic helicoidal trajectory or whatever you can imagine. They really go through the LHC, a part of the LHC lattice. So to go from, and this is the key ingredient of Totem, of any measurement of Totem, to go from the observable physics variables, position, angles, etc., that you measure at the detectors, to the true outgoing angles of the protons as they've been produced at the interaction point, you have to know extremely well the optics of the machine. You have to propagate back the protons through the optics of the machine. And this is what makes one of the most interesting challenges of the Totem measurements. Okay, Totem is a small collaboration with respect to the scale of the large LHC experiments. It has 7 countries. Czech Republic is one of them, 15 institutes, 2 from Czech Republic, order of 100 collaborators and of 80 authors. Construction cost of Totem was of the order of 7 million Swiss francs, and the operation budget is less than $500,000 per year, just to give you the scale. So, some special runs of Totem. We started approaching the beam from very far in 2010, 25 sigmas of distance. Sigma is the transverse size of the beam, and this is particularly telling for us because they were the first candidate elastic events that were detected by Totem at the very beginning in 2010. This is just for history. Of course, at 25 sigma, given the T distribution of the cross-section, you cannot expect a lot of statistics. And okay, we are in standard beam conditions at the time. Then this is already more interesting. As I said before, in principle, what you measure at the detector is not what happened at IP5. Nevertheless, the elastic is an interesting kinematics, has a singularity from the kinematics point of view. So you can expect that the correlation that existed between the angles at IP5 still appears as a correlation before doing any serious analysis, also at the detectors. And indeed, if you plot something that is vaguely proportional to the angle measured at the detector station on the two sides, sector 4.5 and sector 5.6, then when you start to see an island along this diagonal, you start to tag elastic candidates. So the interesting thing that I want to stress here is that the correlation, the typical kinematical correlation existing between the protons at the interaction point, in case of elastic scattering, survives across the LHC lattice, and you still find it at the detector level. Of course, this is prior to any real analysis. Okay, here there is a tabulation of the different runs that have been taken by Totem. As I said before, we have to rely more on special runs. That's why we went to special optics of 90 meters, which were illustrated this morning by Sergio, which is particularly the focus optics to maximize the size and the parallelism of the beams. So this gives us much better acceptance and therefore better access to the elastic T distribution, or to any other T distribution decreasing with T. Okay, I don't want to go to stay too much on that. What is important is what we did this year. On top of the typical Totem standalone runs, This year we started to run together with CMS, taking data with a full detector, working together, and even exchanging triggers. For example, CMS could trigger on the jets, and we could see if we had diffractive protons in the Raman pods. Vice versa, we could trigger on Raman pod coincidences in Totem, again on the two sectors, on the two sides of the interaction point, and see what was measured in the full CMS detector. 25 million events were recorded this year in this configuration. Of course, we hope to do more in future. So let's start to have a look at some first physics results. The first result published by Totem was the elastic scattering differential cross-section for proton-proton. Just a few words to get customized to plots that we will see often. These are just raw data, radiography of what we get as a heat map, as a track map, into the Raman pods at 220 meters. The only thing I want to stress here is that the optics is such that whenever protons have lost their momentum, their longitudinal momentum that we identify as psi, they are deviated by the LHC lattice towards this side. Okay? So, for example, elastic protons, which are supposed to have zero psi, of course, cannot be found here, but must be exactly in this axis. Instead, the T value of your protons can vary along this dimension. So you see that we have two orthogonal dimensions. One gives us directly the T of the proton, the other the psi of the proton. This is particularly interesting, of course, for the elastic scattering. This starts to be interesting for double Pomeroy exchange or single diffraction. Okay? So this is just to have the map always ready in front of us. And as I said before, the tagging then of the elastic is based on the classic kinematics and xi equals 0. This is obvious. Then I cannot describe here the full analysis, but of course you can follow that in the papers, going through all the steps and all the corrections which are required, and the optics itself. I'm going fast on these points, but if there are any questions, you're interested in any specific aspect, we can discuss it at the end. To give you an idea, the optics is reverse engineered in a parameter space of 36 dimensions, which means that within the tolerance of all the LHC values, magnet currents, absolute momentum, and resolution of the momentum, everything are all parameters and that are retrofitted by the Totem data, so that even in the tolerance of the LHC values, we can see what was the best fit. Okay. Then, again, for the analysis, full systematics evaluation. Then an interesting slide so that you see in T and in the sigma dt what are the uncertainties due to statistical and systematic errors. And finally, the first result of Totem, the d sigma dt at 7 TeV. It is particularly interesting because we observed, again, the diffractive minimum after 40 years that it was measured at the ISR. After that, for 40 years, this minimum had never been measured again. So it was the interesting feature. Let's remember that in anti-proton collision at Fermilab, you have only the shoulder, and this comes from really the modeling of a different exponent in the expansion in terms which makes the shoulder because of a sign rather than the dip as it happens in the proton-proton. So there is some theory behind here. Okay, these are the ISR data that you can see for completeness. You see the difference with the proton-antiproton data and the classic diffractive pattern that corresponds to what we measure here. It is particularly interesting, of course, because then it gives hints on the structure of the proton, which, of course, goes beyond this discussion here, but it is really the main physics goal behind that. And this is the result of the uncertainty. Particularly interesting is the position of the dip, which has shifted towards the lower T values in absolute value, as it was predicted and expected from theory and from the ISR. The other interesting feature is the power law of the larger t values that the ISR found surprisingly to be almost constant at power law of 8. This that we found in totem is not representative because you should go up to more or less 8 GB squared to be in standard conditions to measure this power law. We are at much too low t for the moment, but nevertheless you see that the value is quite intriguing there as well. For the exponential law, the exponential slope at low t, here of course you just see the startup, and now we will see it more interestingly in dedicated data. But at least you see anyway the exponential behavior. Most important, the moment that these data were compared to all the theoretical predictions of the model that were on the market, we saw that none of them was getting correctly at the same time the normalization and the key structure, the key positions of the features of the distribution. Nevertheless, the model of Petrov worked remarkably well, and in fact, it was just a matter of little scaling for him. Okay, here there are the details of all the comparisons to the models. And that was the publication, the first paper of Totem, which also went on the same career. Okay, then from the differential cross-section, we can move to the total elastic and inelastic cross-section at 70V, which are already published. And we will concentrate first on the measurement and results, as I said, at 70V. So, a little bit of well-known physics. We apply the optical theorem, and then what you need is to measure just the elastic scattering, extrapolation of elastic scattering to t equals 0 in Totem, if you can rely on a determination of rho from the compete collaboration, which is the preferred value or best fit, whatever you want to call it, that you see doesn't propagate a large uncertainty to the measure of the cross-section the moment that you do the proper error propagation. And, of course, the luminosity that needs to come from an external source. In this case, it is coming from CMS. So we use the determination of the luminosity from CMS for these runs, the rho from the compete fit, and in a first instance, just measuring the elastic scattering features, you can deduce what has to be the total cross-section. Incidentally, let's keep in mind that after you find the total cross-section with the optical theorem, and you have integrated your differential distribution of the elastic scattering yourself, then by subtraction, you have a very interesting determination of the inelastic cross-section. And I say very interesting because it is a fully inclusive inelastic cross-section. You have no dependence on Monte Carlo, no extrapolation to do for single diffraction. It is, or at low mass, it is a fully inclusive inelastic without model dependency. Okay. Then you see that the data now at 90, with the optics of 90 meters look completely different. Same pattern like before, same meaning of psi, t, exactly like before. But you see two interesting features. One is much less background from minimum bias, thanks to the optics at 90 meters. And second, of course, a huge maximization of the signal to background ratio, because the optics of 90 meters de facto parallelizes the beams. So you start to bring to the Raman pots, thanks to the new optical functions of the LHC, you bring to start to the optics, 220 meters far from interaction point, also the protons that were emerging at very low T. So it is really swinging the protons like this, and you get them to the Raman pots at angles that otherwise would be unthinkable. So here the lattice works for you. And to go directly to the results, you see, first of all, these are just the last points. These are just the last points of the previous differential, the lowest T of the differential distribution that you have seen before, plotted with their 1 sigma systematic uncertainty. We had at the time almost 30% of uncertainty on the normalization. And then you see now with the full statistics the evolution of the full B slope at low T. To give you the idea, you see that when we were studying the differential distribution, the differential cross-section, we had T's that were in the lowest case in absolute value at a level of 0.47 or 0.36 GV square, while here we go at 0.02 GV square, and we reach this level here. What does it mean? It means that when you apply the optical theorem, if you want to apply the optical theorem, as I said, first of all, you need to extrapolate this to 0. And as we saw before, you also have now the possibility to integrate the elastic cross-section. And this gives now a first interesting observation on which we will come back later. Point number one, we measure about 2/3 of the cross-section, and we have to extrapolate for 1/3 of it. So, not brilliant, not bad. However, when you want to extrapolate to t equals 0, you must respect two fundamental constraints. One is not to be too close to the dip, to the diffractive minimum, otherwise this brings you an artifact in the determination of the slope of the hadronic amplitude. Second, you should not be at t's which are too low, at a level of 5, or let's say at a level of 10 to the minus 3 or 2 10 to the minus 3, because otherwise you go into the Coulomb interference region, and then again the hadronic slope is alterated. So this is a golden region where you can hope really to detect the hadronic amplitude in purity. Incidentally, it is probably not an accident that trying to fit these experimental points in chunks, in slots, and at the best of our resolution capability, etc., we always found a constant slope. Okay, I try to accelerate, I'm sorry. So, as I promised before, using the optical theorem and the extrapolation to t equals 0, we can determine the total cross-section. This was the first determination of the proton-proton total cross-section at 7 TeV, which was of the order of 98.3 millibards. And as I anticipated before, we could compute by subtraction at that point in time the elastic cross-section, which compares very well within the quarter uncertainties to the previously published inelastic cross-section by CMS, Atlas, and Alice. And as I said, this has the feature of being really fully inclusive. It doesn't depend on any Monte Carlo for extrapolating in the low mass region. And this is important, of course, the moment that you now put the totem measured point here, you really have an interesting lever arm for the evolution of cross-section. This was Fermilab, as you remember, and these are the cosmic rays, and you see how we block this one, the evolution of the cross-section with this point and this very small error. Okay, so this was the result of totem. Publication, etc. Of course, the next step is to avoid any dependence on luminosity, as we have seen before, which dominates the uncertainty. By the way, it is 4% normally. So we have mixed up together several models, several ways to compute, again, the cross-section with newer data. And I don't go into the details here, but the important thing is that one can measure again with the same methods, but with larger bunches, in order not to be dependent on the intensity of the bunch or the number of protons in the bunch, which gives an effect on the precision of the luminosity. Or we can measure with T1 and T2 the inelastic cross-section per se, integrate it, then do the same with elastic, and then we don't depend anymore on rho, but only on the luminosity of CMS. And ultimately, you can apply the optical theorem for the elastic and inelastic observed rates and fully corrected physics rates, and you obtain a luminosity independent measurement. So we can do it in many different ways, every time factorizing out a possible dependence, either on the bunch size or on the rho parameter or on the luminosity of CMS. And I now skip directly to save time. Here you have all the details, and you see that, again, we extended our range to T-means now of the order of 5 10 to the minus 3, so we start to approach a possible Coulomb interference region, another factor 2 or 3, and you get there. But again, we found a constant slope consistent with before, and again, extending the full differential distribution. But what I want to show is this one here. First of all, the rho-independent determination of the total cross-section, consistent with before. Of course, now you see that the luminosity error dominates. And then let me skip to the luminosity-independent result, which is now under publication, which is, again, 98.0 millibarns with the quoted systematics, and now it doesn't depend on the luminosity anymore. Interestingly, since you know the sum and you know the ratio of the inelastic and the elastic, you compute also the elastic and the inelastic in a luminosity independent manner as a byproduct. And this is what I wanted to show instead. This is the summary of all our results on the total cross-section at 7 TeV, which are consistent within the quoted and propagated uncertainties. They have been either published or reported to the LHCC and are under publication. And now I have the pleasure to show also the first public release of the total cross-section at 8 TeV, which was just blessed via internal refereeing in the collaboration last week. And here you see the results. This is an analysis which was driven by one of our groups of Prague, which really had a key role in all the aspects of the analysis. And you see that we have an increase of the total cross-section having moved from 7 to 8 TeV. And again, of course, if you plot it like before, it doesn't give you a huge lever arm, but it is nevertheless interesting. Finally, I would like to conclude with a quick review of the perspectives on the forward and diffractive physics. I will only concentrate on the results in order to gain time. So first, you see that we can measure a full menu of inelastic processes and color-neutral diffractive processes. And let's start with the inelastic processes. Here, Totem measured the dn d-eta distribution, so the charged dn d-eta distribution, like the other experiments, but in the specific eta range of Totem, so of T2 in this case. You see that, again, none of the models could predict at the same time the slope and the normalization. You see our data here. Now, the data at 7 TeV have a chance to be combined with the ones of Alice to have data coverage, while the data for 8 TeV, they have been taken directly together with CMS and will be published together with CMS. However, you see that if the current results of the current publications are put together with all the caveats that you know, okay, in terms of trigger constraints, etc., you see that the results give already an idea of how the final rapidity range might look like. And then just final word on the central diffraction and single diffraction. You can see here qualitatively that we can put in vitro a telescope and measure the multiplicities on the opposite side of the interaction point depending on the size of the protons that we measure in the Raman pots. This is for single diffraction at small or large size. The same for double Pomeroy exchange and central diffraction, where we can use CMS as a full detector together with us. And just the final slide, I just want to show as a proof of concept that we are able to constrain the T2 rapidity range with T2, the rapidity ranges and the rapidity gaps that you can expect in the telescopes or in CMS, together with the size that we measure with the protons in the Raman pots, and therefore reconstruct a mass distribution this way. More interestingly, when we will really combine the data, and now we have taken the data together with CMS, we will be able also to access R diffraction, so with jet production. And I just show you the first two jets, which have been reconstructed, the first two dijets, which have been reconstructed in CMS independently and with the size of the protons in Totem. And although it is still to be taken with caution, uncorrected results, but you see as a proof of concept the kind of physics that we can explore together. The key message there is that with the protons of Totem, you will know the initial state, and you bring back the LHC to be a gluon-gluon or a lap-like machine where you know the initial state, and then you see what you find in CMS. So in terms of all the talks that have been made about the key importance for the future of the missing energy in the central detectors, this is an interesting tool that we plan to exploit. Thank you.
The speaker, and the floor is open for discussion. Questions, please. Yes, please.
Can you access the region of interference with Coulomb and get rho?
Yes, this is the next step. Now we have been running this week with an optics which is even more pushed than the one at 90 meter. So we are running at 1,000 meter, 1 kilometer, and with these optics we on purpose are going to scan the full interference region. And rho, of course, is one of the parameters that we want to take out, but also the features of the interference that we want to look at may, in particular for the phase, not only for the amplitude, are things that can hide even more surprises than rho, which is expected more or less to have a known or understood dependence on S, while for the phase is a different story.
Another question? So if not, we thank the speaker again.